Okay, so now that we've actually set up the models, how do we go about solving them? So we are only going to investigate one case of solving them, which is the graphical method. There are many other computational methods available, but the idea behind this is just to give you some understanding of how these methods work so you can interpret the results. Usually you'll use software to do it. So to solve it graphically, what you're going to do is you're going to plot the constraints. So you first plot the constraints as straight lines. Because they're linear, they are straight lines. So you have your choices on how you're going to plot the constraints. You can either find the x and y intercept and then connect the dots to the line kind of situation, or you can put the constraint in the form of y equals mx plus c and then plot the y-intercept and utilize the gradient to find that second point. However you want to draw the line, go for it. Then you're going to look for where the constraints are actually met. So all these constraints are less than equal to or greater than equal to or equal to. Obviously, if they're equal to, just the line is where the constraint is met. But if they're greater than or equal to, it's either going to be above or below the line. So there are two ways to go about this. The one is you can actually just say, for example, you have a constraint that chills like that. You can select a point over here, any point, and test it inside the constraint equation. And then if it actually fits the constraint, in other words, say you had x plus y must be less than or equal to 16, just a random kind of constraint, and you have this is 3 and this is 3, and we put that in, we have 3 plus 3 is less than or equal to 16. It does meet the constraint, so everything below the line then meets the constraint. So you basically choose a point in one of the regions, either above or below the line, and check if it meets the constraint. Obviously, if it doesn't, then it's the opposite side that meets the constraint. Another way that you can go about doing it is actually just to set your constraint into the form of y equals mx plus c and look at that less than or equal to sign, because when you have something like y is less than or equal to 3x plus 4, again I'm just choosing a random kind of constraint, what this is saying is here you have a straight line and it's saying all the y values which is less than that straight line. So then it's automatically telling you it's underneath that line. So those are the two ways that you can approach it, and obviously we're going to look at those ways when we go and actually set up and solve the problem. So one of the things we're going to do now is we're just going to plot a random constraint just to make sure you know how to plot straight lines and stuff, and then move on. Okay, we're just going to look at a quick guide to plotting your constraint. It's basically plotting straight lines, so it's something you should be comfortable with, but if not, let's just recap it. So let's have a constraint that is just 7x plus 4y is less than or equal to 4. There's a couple of ways you can plot a straight line. You can find the x and the y-intercept and then just connect the dots kind of a situation, or you can find the equation of a straight line. So just a reminder, the equation of the straight line is y equals mx plus c. So in other words, your y is your subject of your formula and everything else is on the other side. And then you have your m, which is your gradient, which is your change in y over your change in x. And then you have your c, which is your y-intercept. Now, if we were going to follow the approach of finding your x and your y-intercepts, which is the slightly easier way when you're drawing your line to double check, also helps if you need to scale your image correctly. Knowing all the intercepts helps you in determining your scale of your image or your graph actually. So let's just go ahead and work out the x and the y-intercepts. So the x-intercept is where y is equal to 0. So in other words, we take the 7x and then we make y equal to 0, so we have 0 there, and it's actually equal to 4, but I'm going to leave it as less than or equal to 4 so that you can actually just see what exactly is going on. So again, when we're working this out, it can be equal to, okay, and then we say 7x is equal to 4, and x is equal to 4 upon 7. So our x-intercept is going to be at 4 upon 7. Then we can look for our y-intercept, and our y-intercept is going to be where x is equal to 0. So we can again take our equation, 7x plus 4y equal to 4, and then we are going to take the x and make that equal to 0 and solve for our y. So we have 4y is equal to 4, so y is equal to 1. So now when we're plotting on the graph, we know that we're going to have an intercept at x is equal to 4 upon 7 and an intercept at y is equal to 1. So then again, we have, our y and our x. We would obviously work this to scale. So I'm going to be a little bit cheeky here. I'm not going to do it fully to scale, where I'm going to be like, okay, that's 0.5, that's 1 kind of a situation. That's 0.5 and that's 1. I know that obviously this, where y is equal to 1, we're going to have an intercept. Okay, and again, you're going to have this to scale, but I'm just going to guesstimate it just a little bit. So this was 0.5, right? And that's 1. Let's just make 1, 2, 3, 4. So 0.6, 0.7, 7.8, 0.9, and 1. Again, should be to scale. I'm using a tablet, so bear with me on this. So 4 over 7 is 0.57. So it will be sitting somewhere over here. It's not quite 0.6. And then we just, connect the dots, obviously using a ruler preferably to have the line occurring. Not preferably, you should really be using a ruler. Okay, so that is one way to draw your line. Now, one of the reasons why I actually like making the line in the actual line formula of y equals mx plus c is it's going to also help determine, where the constraint is, whether it is above or below the line. So at this point, if you had just done the x-intercept and the y-intercept, you still need to figure out if it's everything above the line or everything below the line. And the easiest way to do it, in my opinion, is you actually just make y the subject of the formula. So let's actually go take this constraint and make y the subject of the formula to make it into this y equals mx plus c. So if we do that, we have, okay, let's just rewrite it. 7x, 4y less than equal to 4. We have 4y is less than equal to minus 7x plus 4. So we have y is less than equal to minus 7 over 4 x plus 4 upon 4, which is just 1. So we have y is less than equal to minus 7 upon 4 x plus 1. Okay, and if we had done this, we could have plotted our line straight from this as well, because we would have seen that the y-intercept is 1, so we would have had this 1 over here. And then we could have used the idea that it's the change in y of the change in x. So if we were looking at the change in y over the change in x, we'd have a situation that if we go 7 down and 4 towards the right, we would have a dot, basically. So my graph is a little bit too small to do that, but you would take 7 units down and 4 towards the right, and you'll have a dot that is on the line. And then you could just connect those two dots, and you would have it passing through here anyway. However, if you don't want to do that, that's perfectly okay. The main reason why we like this y is as the subject of the formula is because we can read directly off this whether it's above or below your line. Because here it says y must be less than equal to the line. So it's all the y points that is less than this red line. So in other words, it's all of this over here is what is actually fitting our constraint. So we can automatically read off from if you make y the subject of the formula. If you don't make y the subject of the formula, there is a few ways that you can go about it. I do understand that you'll immediately look at the constraint and go, well, 7x plus 4y is less than equal to 4, and therefore it's underneath the line. That is not necessarily always the case, because the sign is going to make a difference. So the sign is going to make a huge difference in regards to that, and I'll do an example to show you that. So the other way that you could do it is you actually take a point on either side of the line. So you take one point. It can be on this side of the line, or it can be on this side of the line. And you just choose a point. I'm going to choose 0 and 0 because I'm lazy, and frankly, you should be too in regards to this. So 0 and 0 sits on this side of the line. And then I put it into my constraint. So I say, okay, 7 times 0 plus 4 times 0 is equal to 0. Is 0 less than equal to 4? Yes, it is. And therefore, it's everything on this side of the line. If I had tested it on the other side of the line, for example, and I chose 1 and 1, again, be as lazy as possible, make it something easy that you can do the maths for, and remember that was 1 and that's 1 there, and then I put it into the equation, so I have 7 times 1 plus 4 times 1. Well, 7 plus 4 gives us 11, and 11 is not less than 4. So everything on this side is not fitting the constraint. And that's how you can work it out, by just choosing points. So we've covered 3 different things here. We've covered drawing the line by using the x and the y intercept. We've briefly looked at the idea of drawing the line utilizing y equals mx plus c. And the idea is you have your y-intercept, and then you have your changing y, your changing x, and you can find a point on your graph in that manner. We've also looked at the idea that you can find where the constraint is by, if you utilize the y as the subject of the formula version, directly reading it off that from less than or greater than. So y must be less than, so it's all values of y less than, so it's underneath the line. And if it was y greater than, it would be all values, above the line. And then we've also looked at the point of, if you're still not sure or you're not happy with those approaches, you can take a point on either side of the line, or one point on the one side of the line, check it. If it matches the conditions, then everything on that side of the line is where the constraint is being met. Okay, so I'm going to use the Desmos graphing calculator just to show you the different constraints and how exactly they work. So we have gone through how to actually, plot it, going through the working out where it is above the line and where it's below the line. But let's just go through the process of taking that constraint that we just played around with, 7x plus 4y less than or equal to 4. So right now what this does is it shades in everywhere where 7x plus 4y is less than or equal to 4. So everything in red currently is what fits that constraint. So again, particularly when we're doing this whole process, you could choose either to shade in the region where the constraint is met, or you can choose to shade in the region where the constraint is not met. But the moment you choose one version of it, so if you decide to color in the region where the constraint is met, obviously for all the rest of your conditions, you're going to do the same thing. And if you choose to do it in the other direction, obviously, again, bear in mind, you must just be consistent. So another way to look at this is, and this is just using the Desmos calculator, you switch the sign so that it shades in the other region. So now we have everything in the white side is where the constraint is being met. Okay, so again, this is just, the calculator is just there to, the Desmos graphing calculator is just there to help you particularly learn how to plot your lines so you can practice and stuff like that, and then how exactly to work it out. You can type in your constraints exactly as is. You could also type in your constraint as you've worked out the line, so utilizing the y equals mx plus c version of the line. So just to illustrate that point to you, there is the original line. Let's just also change our less than or equal to back there, because remember our original constraint was 7x plus 4y is less than or equal to 4. So everything that's shaded in is the region of the line. And just to confirm that if you actually go ahead and do your line as is with getting the gradient and getting the y-intercept, again, there it is, directly over it. So that's just in case you didn't believe me kind of situation. Okay, so I just want to investigate particularly the above and below the line situation, just so that you understand why you don't just read it straight off the constraint, and why making y the subject of the formula makes it a lot quicker for you. So let's just take our original constraint. So we have that 7x plus 4y less than or equal to 4. And at the moment you may be thinking, okay, well, the less than sign tells me it's underneath. And now I'm going to show you why this is not actually always the case. So we've already investigated this. So you have, again, we're just going to make y the subject of the formula. So we have 4y is less than or equal to 4. So we have 4y is less than or equal to minus 7x plus 4. So we have y is less than or equal to minus 7 over 4x plus 1. And that told us that it was everything underneath the line. Now I'm going to show, again, reasons why you don't just automatically read it from the constraint. So let's take another constraint that looks very, very similar to this one. 7x minus 4y is less than or equal to 4. Now, if you were just going with the assumption of the less than sign means underneath the line, I'm going to show you why that doesn't always work. So again, let's make y the subject of the formula. So we say 7x minus 4y is less than or equal to 4. So we have minus 4y is less than or equal to minus 7x plus 4. And then we're going to multiply through by 1 over minus 4. And when we multiply through by a minus sign, our inequality switches over. So we end up with y is greater than or equal to 7 over 4x minus 1. So now we know it's everything above the line. Okay, and again, if you weren't following or you're not sure how we get from this one to this one, we can do it in a slightly different way. So here we can actually take minus 4y across to the other side. So we're going to take it across the other side there. So we're left with 0 less than or equal to minus 7x plus 4 plus 4y. And then we're going to take the 7x and this 4 across. So you're left with 7x minus 4 is less than or equal to 4y. Then we divide through by 4, so we have 7 over 4x minus 4 upon 4, which is 1, less than or equal to y. And then we just make y the subject of the formula. So we have that situation. And again, the fact that we're looking at all the y's which is greater than this part, it is above the line. So again, just be very, very careful, particularly when you're trying to find where the constraint conditions are met, to not just blankly, approach it by just looking at it from the constraint angle. It's going to be dependent on your sign over here and the inequality sign. So the easier way to just not make those mistakes is to actually just go ahead and find y as the subject of the formula. So now you've reached the point where you can plot the individual constraints, and there are going to be regions obviously where the constraints are met. So the idea is that not all the points in the xy plane is going to satisfy those constraints, and those that do satisfy the constraints is going to be contained in a special set. And this set is basically referred to as a feasibility region. In other words, it's the area where all the constraints are actually met and all the sign restrictions. So usually you'll end up in a situation of, say you have like 2 constraints like that, and say for example, it's not met on that side and it's not met on that side of this line. Then you'll have a feasible region which is sitting over here. Y over there is because you usually have x and y must be greater than or equal to 0. So in other words, this part of the quadrant doesn't really exist. Okay, so we're only working in the first quadrant. The idea behind this is, or what you need to understand about this is, there is mathematical work that basically says that when you have a feasible region, and your region is obviously made up of the joining of the constraint lines, all those extreme points, which are corner points essentially, so these points shooting over here and over here and over here and over here, they are going to be where the optimal solution of your problem is going to be found. And there is a lot of reasons behind it. It's to do with the fact that there are convex sets, and the fact that your objective function is going to be tangent to this feasible region, which is a convex set. You don't have to overly stress about that. We're not going to go into too much detail about it. But the thing that you're going to be remembering is that all that creates the corner point theorem. And the corner point theorem basically says that if a linear programming problem has an optimal solution, that is, if it has a maximum or minimum, then it must occur at a corner point of the feasibility region. And this is whether or not the feasibility region is bounded or unbounded. I'll speak about that now. However, if it is unbounded, then your optimal solution may not exist. So if it's bounded, an optimal solution exists. And if an optimal solution exists, it's going to be sitting at one of these corner points. Again, going back to like that one there, that is a bounded situation. It's bounded when you can draw like a circle around it, and it has no other points. Again, I'm really simplifying this. And unbounded is a situation where you can't really draw the circle around it, but again, if an optimal solution exists, it will be at a corner point. So let's just have a quick look at unbounded and bounded, just so you can get an idea behind it. Okay, so on the screen is 2 types of feasibility regions. As you can see, again, I'm not putting in the details of mathematics for this, just kind of like see that it is bounded. You can it is contained basically. And when you have an optimal solution in this problem, it is going to exist at one of these corner points. And then you have a situation here that is an unbounded region. You can see it kind of goes off into, infinity and infinity that side. But if an optimal solution was to exist, it will exist at this point and this point. So again, one of the most important things to understand about the corner point theorem is the optimal solution of your linear programming problem will exist at the corner point or the extreme point. Okay, so now we're going to take that maximized example that we created the mathematical model for, and we are going to set it up to solve the linear programming problem. In other words, we're going to take all the constraints, we're going to draw them on a graph, we're going to determine the regions in which the constraints is met, so we can determine our feasible region, that area where all the constraints are met. Then we're going to look at the corner points of those feasible regions, and then we're going to take those corner points and substitute them into our objective function and solve the objective function value there. And in this case, we're going to find the maximum of it. Okay, so that's the method that we utilize and approach. There is another method where you have the objective function and then you increase its y-intercept, basically moving the objective function along the quadrant or first quadrant that we're looking at until it is tangent to the feasible region. And the first one is its minimum, and as it moves on, the last corner point, in which is a tangent to the feasible region, is its maximum. However, we do not utilize that approach. I will, however, discuss it right after we've done all the solving in this problem, because it's going to come in very useful when you're looking at the range of optimality. So again, here we have the problem. Let's actually just number our constraints so that when we work with it, we know what we're talking about. So constraint 1 is going to be the manufacturing hours constraint. And then we're going to have constraint 2 is going to be the testing hours constraint, which is the 360 hours. We're then going to have constraint 3, which is the production amount for the minus models, the production kind of constraint. And then we're just going to quickly do things so that you remember this. Your x greater than or equal to 0 is going to be constraint 4, and your y greater than or equal to 0 is going to be constraint 5. You're going to need to remember to always put in your non-negativity constraints because that limits you to the first quadrant. Okay, so now we're going to work with constraint 1. We're going to put down all the information we need to draw that line, and we're going to do that for constraint 2 and 3, and then we're going to do the drawing just to make it a little bit easier on us. So we're going to just get all the information we need to plot the graph. And that is a good idea for you to do anyway, because you are going to need to draw your graphs to scale. So if you have the information of the x and the y intercepts, it's going to help you figure out how big or small your graph needs to be and what the scale of your graph of your units of your graph should be, so that you fit everything onto your graph in itself. Okay, so let's move on to working it out. So to begin with, we're going to work with constraint 1, which is your 10x plus your 8y is less than or equal to 800. So the easiest approach, particularly, so that you can work out your scale of your graph, is actually to find the x and the y intercepts. So let's go ahead and do that. So the x-intercept is where y is equal to 0. Okay, so we're going to take our constraint, that 10x plus 8y less than or equal to 800. We're going to write it, as just an equality, plus 8y is equal to 800. And we're going to set y to be 0. So we're just going to set that to be 0 and solve for x. So now we have 10x is equal to 800. X is equal to 800 divided by 10, which is going to give us 80. So the x-intercept is where x is equal to 80. Then we're going to do the same for the y-intercept. In other words, we're going to say let x be equal to 0. So the y-intercept, let x equal to 0. And we're going to again go through the working out. So we're going to say, okay, 10 times 0 plus 8y is equal to 800. So we have 8y is equal to 800. So we have y is equal to 100. So now we have enough information to draw our line. Now, I personally like looking at, for my regions of where the constraints are met, by making y the subject of the formula. I've already explained my reasons of why I prefer that by when we looked at plotting the constraints, just the basic one constraint situation. So I'm going to do that now anyway. So I'm going to make y the subject of the formula, Again, if you just did this one here, you could have plotted your line straight from it. So if you have the x and the y intercepts, it is really useful for drawing the scale of your graph, but you could just draw it straight from making y the subject of the formula. So let's go ahead and do that. We have 10x plus 8y is less than or equal to 800. So we have 8y is less than or equal to minus 10x plus 800. And then we divide through by 8. So we have minus 10 over 8x plus 100. Okay, so that is all our first constraint. And I'm just going to put the number 1 over there. So next up, we're going to have to do for constraint 2. So constraint 2 is going to be 3x plus 4y is less than or equal to 360. So again, we're going to find the x-intercept and the y-intercept. So to find the x-intercept, we have y is equal to 0. So we're going to go through the working out of it. And we're going to have 3x plus 4 times 0 is equal to 360. We're then going to have 3x is equal to 360. And then x is equal to 360 divided by 3, which is 120. Okay? Then we're going to move on to the y-intercept. So we're going to say, okay, the y-intercept is where x is equal to 0. And we're going to solve for it. So if we go ahead and solve for it, we have 3 times 0 plus 4y is equal to 360. So we have 4y is equal to 360. So we have y is equal to 360 divided by 4, which is equal to 90. So now we have our y-intercept as well. And again, we're going to just do the same situation where we make y the subject of the formula for reasons I've already explained before. So y is the subject of the formula. We have 3x plus 4y less than or equal to 360. So we have 4y is less than or equal to minus 3x plus 360. So we have y is less than or equal to minus 3 upon 4x plus 360. Okay, and so we've done constraint 2. We now also need to work out for constraint 3. Constraint 3, luckily, is an easy one. So constraint 3 is y is greater than or equal to 60. And the nice thing about this is when we go through and work out our x-intercept, well, y is equal to 60. It doesn't have an x-intercept, so we leave that one out. We have, again, a y-intercept is where y is equal to 60. And then we look at making y the subject of the formula. It's already done. It's like literally built into there that y must be greater than or equal to 60. So you're going to have a straight line where y is equal to 60. And now we can go ahead and don't forget that you have constraint 4 and 5. 4 and 5 is where x is greater than or equal to 0, and 5 is where y is greater than or equal to 0. So now we have all the constraints, all the information about the x-intercepts, the y-intercepts, and whether or not it is above or below the line. So we can now go and draw the graph. Okay, so obviously when we are drawing the graph, we want to have the information available to us, like right where we are doing it. So let's just quickly write down the main points that we need to just draw the straight lines. So we have constraint 1, remember, it has the x-intercept equals to 80, and the y-intercept equal to 100. In other words, that is point 80 and 0, and that is point 0 and 100. Okay, we also want to add in for the second constraint. So the second constraint, again, remember it had x-intercept of 120 and a y-intercept of 90. And again, that's point 120 and 0, and then that's point 0 and 90. For the third constraint, we had a y-intercept of 60, and it was a straight line, so that's the only thing that we have available to it. So we have 0 and 60. Okay, oh, and let's not forget, just to remind ourselves, you know, for our 4 and our 5, it's going to be a straight line. So 4 is where x is greater than or equal to 0. So it's going to be a straight line where y is equal to 0, basically. And then your y greater than or equal to 0, it's a straight line where your x is equal to 0. So that's what we have to have on a graph. So obviously, if you're doing this on paper or you're doing it, you know, well, you're doing it by hand, you will need to at least have your scales such that you can fit your x-intercepts and your y-intercepts on the graph. and have it clear enough so that you can actually, see what exactly is going on. So in our case, our highest x value is 120, so we want to have it so that when we are drawing this, in our graph, that we'll at least be able to fit 120 into this. Okay, so again, bearing in mind, obviously, if you're doing this on graph paper or you're doing it, by hand with rulers, you're going to be exact with your scale. Pretend I'm being exact with my scale and say that I'm using like 12 centimeters to be my 120, so that, every 1 centimeter is like 10 units. Because then you can easily, see what is going on with, particularly if you have in-between values, like to acknowledge that it is an in-between value. So pretend there, it's nice solid, like 1 centimeter per thing. So you have 10, we have 20, we have 30, we have 40, 50, 60, and again, use your ruler, 70, 80, 90, 100, 110, and 120. Okay, and again, you would make sure that your scale is reasonable also for your y-axis. I'm going to use the exact same scale because my y goes up to 100, so, and it's approximately the same length, kind of a situation. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And again, I'm just going to remind you, I'm going to be kind of obsessive about this. Make sure that when you are drawing it such that, the scale is consistent, and use a ruler. Though I will also be showing you that when we do this, we will be working out our corner points instead of just reading off the graph, because our graph can be inaccurate. Okay, so now we have, our kind of like the scale that we need. We could have gone one further from like 120 and one further from 100, just so that we have, sufficient space, but we can go from here. So now our first line, we have x is equal to 80, so the spot like over there, and then y is equal to 100, so that spot over there. And then we're going to connect our dots. So obviously, again, I'm working on a tablet, so it's not going to come up very nicely. You can see all the bumps happening there. My bad. Let's try this one more time. So pretend that is a straight line. You get the idea. Use a ruler, make the line straight. I'm doing this kind of freehand, so just bear with me with this. So that is your constraint 1. I like labeling my constraints just so that I am aware of which one I am actually talking about. Okay, so then we have constraint 2. Constraint 2 has x-intercept of 120 and y-intercept of 90. So we have that 120 and we have that 90 situation, and we again just connect the dots, basically, the points on the graph. So we'll have something like that. Okay, that was really badly drawn. It's not going through 120. Let's do this one more time. Okay, you get the kind of idea. Again, please use a ruler. Remember, I'm working on a tablet, so mine is not going to be very clear. Be consistent and all that kind of stuff. Okay, so we have those two lines, and again, label it constraint 2. Obviously, I'm working in colors, so I can immediately see my constraints, but you may not necessarily be working in color at home, so just like bear that in mind. Okay, then we have y is equal to 60. So y is equal to 60 is going to cut across there, but it is a straight horizontal line. So it's just going to pretty much just chill all the way through here. So it's going to be something like that. So it's going to go in that direction, and it's going to go in that direction. And then we have our y is equal to 0, and then our x is equal to 0. So that just is firmly putting us, in this first quadrant. But this is, I'm just doing this to remind you kind of a situation. Okay, now we are going to do the above and the below the line situation to make sure. So there's a couple ways that we can go about doing this. I'm going to do it very specifically so that my feasible region becomes the white region, mainly because I feel it gets kind of overcomplicated when you end up shading in the whole feasible region so that you can see what it is. So I do it in the direction where I shade what is not feasible, kind of like crossing out, so that my feasible region becomes, that nice clear white region that you can see on your piece of paper. So we're going to go ahead and do this. So I use the approach where we've written the line in such a way that y is a subject of the formula, so we can already see whether it's above or below the line. But just to remind you about it, so remember constraint 1 was y is less than or equal to minus 10 upon 8x plus 100. So everything underneath the line is going to be feasible. By that we're looking at, so everything underneath this line is feasible. So everything above the line is not. So I go, okay, this is not feasible. And I do the shading situation. Okay. Next up, we are going to, oh, should not have done that. Put back my green line quickly. I just wanted to clear the screen a bit so that you could see what am I referring to. Okay, so I'm just removing the yellow arrows just so you can see. So now we go to the green line, which is constraint 2. So in constraint 2, we have y must be less than or equal to minus 3 upon 4 x plus 90. So again, it's everything underneath the line. So underneath this green line is feasible. So everything above the line is not feasible. So we're just going to scratch that out. And we do the hatching in a slightly different direction to the previous hatching. Okay, so you would particularly do that if you're going to end up shading the region which is feasible, so you can see where all the hatching is actually together, that it's the feasible region. Again, I prefer this method purely so that I don't have to stress about making sure that the region I'm looking at is the feasible region with all the different hatching. Okay, so now we've done that. Now we look at constraint 3. So constraint 3 says y must be greater than or equal to 60. So for constraint 3, everything above this blue line is feasible. So everything below it is not. So again, we go ahead and do the scratching. I'm going to make it all horizontal to make my life a little bit easier. Okay, and then we do the rest of it. So the y must be greater than or equal to 0, and x must be greater than or equal to 0. So if we go and do that, so we first do y must be equal to 0 situation, that line, which is the line that's currently displaying the red line. We say, okay, well, x must be greater than or equal to 0. That means everything above the red line is feasible, which means all of this is not. And again, that's just restricting your quadrants. We're just doing this just as an in-case kind of factor. Then we also have the case where constraint 5, where y must be greater than or equal to, okay, I wrote this wrong. I'm sorry, I'm not going to redo this part. Y must be greater than or equal to 0. That's what we've just covered. We've looked at that and gone, okay, everything below the line is infeasible. Then we're going to look at where x is greater than or equal to 0. I realize I have switched it around there with my constraint 4 and 5. I'm sorry, let's just not stress too much about that. We have x is greater than or equal to 0, which means it is going to be everything. When you take your y horizontal line, this line over here where I'm doing the hatch of, this line here, it is going to be everything in that direction is feasible. So we're going to cross it out. So we cross it out. Okay, and again, it is sitting there for the quadrant. Okay, so now we actually look at what is our feasible region, and we indicate it to the user reader. So this white area is our feasible region. Okay, and that means that all at our corner points of this feasible region are our possible optimal solutions. So let's just identify our corner points. I'm going to use the yellow to do that. So let's just take that yellow away. So this point over here, this point over here, this point over here, and this point over here. So one of the nice things is this point over here is your y-intercept. You already have what this value is. You know that it is 0 and 90. You also have this value over here. You know that it is 0 and 60 because it is intercept. Now, traditionally, possibly at schools and stuff, you were told, okay, you can just take this value, these values off the graph. Don't do that, because reading off your graph is going to bring in inaccuracies to your data. So you're going to actually solve the simultaneous equations to find where they intersect to get these 2 points. So you're going to use simultaneous equations to find the corner points. So we're going to label this A, and we're going to label this B, and we're going to go find them, kind of a situation. Okay, let's not label them A and B, because we already have A and B for other things. We're just going to label this corner point 3 and corner point 4. And we're going to find them. How are we going to find them? Well, we know that it is where the green and the purple one intersect for corner point 3. So corner point 3 is where the green one is constraint 2, is equal to the purple constraint. What is the purple constraint? It is constraint 1. And then you have corner point 4 is where your blue constraint, in other words, your number 3 constraint, is equal to your purple constraint, which is the number 1 constraint. So you will solve the simultaneous equations for both of those to find those corner points. So let's go ahead and do that. Okay, so we're going to go through finding corner point 3. So corner point 3 is where your 1 is equal to your 2. So constraint 1 is equal to constraint 2. So there's a few ways that you can go about doing this, but let me first just remind you what constraint 1 and constraint 2 is. So constraint 1 was 10x, let's go back there, 10x plus 8y is less than or equal to 800, and constraint 2 was 3x plus 4y less than or equal to 360. So those are the constraints we're working with, and we're going to do simultaneous equations. There's a couple simultaneous equation methods that we can approach. I'm going to look at 2 of them. You can obviously choose whichever one you're comfortable with. So one of the things I remember is that we technically made y the subject of the formula for both of these. So we have equations where y is the subject of the formula already. So we have y was less than or equal to minus 10 upon 8x plus 100, and that's chilling that one over there. And we had, for constraint 2, y was less than or equal to minus 3 upon 4x plus 90. So the thing is, we know it's where 1 is equal to 2. In other words, the y values are the same. So we could automatically, in this scenario, take it as minus 10 upon 8x plus 100 is equal to minus 3 upon 4x plus 90, and then solve for the x value. So if you go ahead and do that, we're going to put all the x's on one side, all the constants on the other side. So we have 100 minus the 90, in other words, the 90 is going to cross to the left-hand side. Then we have minus 3 upon 4x plus 10 upon 8x. So we have that gone to the other side, and becomes plus, obviously, because it was minus on the previous side. Okay, so then we have 10 is equal to, and we can just put it into our calculator, but we're going to just do this in our heads. So we make this 4 and 8, and we do that by multiplying by 2 over 2. So that gives us minus 6 upon 8x plus 10 upon 8x, which gives us 4 upon 8x is equal to 10. I'm just moving it a little closer so that we can see what's happening. And we know that 4 upon 8 is a half, so just some in-between steps which aren't necessary. Remember, I will do extra steps. You don't have to do all the steps. And then we multiply by 2, so we get x is equal to 20. So therefore x is equal to 20. Then we use x, so we substitute in x into either 1 or 2. So into 1, if we go ahead and do that, we have y is equal to minus 10 upon 8, 20 plus 100. We go and do this, it's minus 200 upon 8 plus 800 upon 8. Why is that? Because we had 100 there, we're just making it over the denominator 8 so that we can do lazy math. And we have 600 upon 8, which is also equal to 75, just by the way. And so we have our corner point for corner point 3 as 20 and 75. Okay, so next up, well, we're going to do a slightly different method to solve for this. So the slightly different method to solve for this is we can utilize direct from our constraint 1 and our constraint 2. So if we go ahead and do that, so I'm doing an alternative method here, we just take this 10x plus this 8y, we make it equal to 800, because we are working on the line, that line where it is actually equal to 800, and we have 3x plus 4y is equal to 360, and then we do the situation, you know, when you're looking at the top minus the bottom, and we need to get rid of either the x or the y. The y in this case is a little bit easier to get rid of because you can just multiply the bottom row by 2. So you can say multiply that by 2 and you get 6 and you get 8, and then you get 360 times by 2, which is 720. And then we can actually take the first equation minus the second equation, so we can minus them. And if we do that, so in other words, I'm just going to rewrite it so you can actually see what's happening. We have the 10x plus the 8y is equal to 800. We now have 6x plus 8y is equal to 720. And now we say, okay, 1 minus 2. So we have this becomes a minus, this becomes a minus, and that becomes a minus. So then we read down, and we have 10x minus 6x gives us 4x. Obviously, 8y minus 8y gives you 0. Then we have 800 minus 720 gives us 80. And then we can solve for x. So now we have 4x is equal to 80. So x is equal to 80 divided by 4. Therefore, x is equal to 20. And then again, we do pretty much what we did previously, where we say substitute. And yes, those are my T's. I know my handwriting is getting a bit bad there. X is equal to 20 into either 1 or 2. It doesn't make a difference. I'm going to do it into 1 again just to make our lives easier. And my 1 here, I can use this 10 times 20 plus 8 times y is equal to 800. 10 times 20 is 200, so we have 200 plus 8y is equal to 800. So you have 8y is equal to 600. That's 800 minus 200 gives you 600. So y is equal to 600 divided by 8, which we know is 75. So again, we have that corner point coming out of 20 and 75. So the choice of the method is up to you. From this point onwards, I'll just do one method. You can choose whichever method you want to do, as long as you get in the correct answers. Okay, so next we have to work out for constraint, or corner point 4. So corner point 4 is where 1 is equal to 3. So a reminder what constraint 1 was. Constraint 1 was 10x plus 8y is less than or equal to 800. And constraint 3 was y must be greater than or equal to 60. So again, a reminder, because we did make y the such the formula in the previous ones. So we had y was less than or equal to minus 10 upon 8x plus 100. And y is equal to 60 is pretty much just what constraint 3 is. So this one's a little bit easier to work out because you don't have to do drastic simultaneous equations. In this case, you can just substitute in y equal to 60 into 1. So if we go ahead and do that, and again, you can choose to either put it into y is equal to minus 10 upon 8x plus 100, or you can put it into 10x plus 8y is equal to 800. Choose whichever one makes your life easier. And I realize my 800 looks like 100, so let's just rewrite that quickly. Choose whichever one is going to make your life easier. I'm going to choose the second version of this equation. So if I do that, I can then just have 10x plus 860 is equal to 800. And then I have my 10x is equal to 800 minus 8 times 60. And let's actually work out what 8 times 60 is. 8 times 60 is equal to 480. So we have 800 minus 480. So let's just fix that level up there. So we have 800 minus 480 gives us 320. So we have the 320 situation there. We have 10x. So x is equal to 320 divided by 10, which is equal to 32. So now we have x is equal to 32. We know that y is equal to 60. So we already have our corner point. So we have 32 and 60 as our corner point 4. We're not done yet though, because remember the whole idea behind the corner point theorem was it said the optimal solution is at the corner point, but now we don't know which corner point the optimal solution is at. So now we get to take our objective function and substitute in all our corner points and solve for our objective function. So in other words, in this case, it is to do with profit. So we are going to solve for the profit, and the idea behind it is we wanted the maximum. So we're going to then look for the biggest value that which the corner points produce. So let's go ahead to a fresh page to go and do that. Okay, so just a reminder where we're at. We had our diagram basically. It was, again, I'm just going to do a super rough sketch of this, where we had a line like that, and then a line kind of like that. And we had our feasible region, this region over here. And we have the 4 corner points. 1, 2, 3, 4. And this was corner point 3. This was corner point 4. We didn't actually label the other corner points, so let's just go ahead and do that. Let's make this corner point 1, make this corner point 2. So now we have those 4 corner points. So just a reminder what those corner points are. We have corner point 1 is 0 and 90. We have corner point 2 is 0 and 60. We have corner point 3, that's the one that we calculated with simultaneous equations with 1 is equal to 2. That was 20 and 75. And then we had corner point 4, which was where we worked out the simultaneous equations, where equation constraint 1 was equal to constraint 3, and we got 32 and 60. Okay, so we have those 4 corner points. Now we have to remember what our objective function was. So remember our objective function, or our objective, let's start with that, was to maximize the profit. Okay, where our profit equation was P is equal to 200x plus 270y. And remember the whole idea behind the corner point theorem was the optimal solution is at the corner points. So now we have to investigate which corner point the optimal solution is at, which means we substitute in all the corner points and we solve for the profit. So let's go ahead and do that. So we say the profit, and remember, just a reminder that this here is actually, P is a function of x and y. So when we write it, we could write it like this, plus 270y. So when I'm solving it, I'm going to do it like that so I actually remember what's going on. So we say 0 and 90. So now we have 200 times 0 plus 270 times 90. And we go and work that out. So we can just put it in our calculator. I'm going to be a bit lazy about this. And that gives you 24300. So then we move on to the next corner point, 0 and 60. Okay, and you put in that, we have 200 times 0 plus 270 times 60. And that's going to give us 16200. Then we go and put in for the next corner point. So we have 20 and 75. That's 200 times 20 plus 270 times 75. And that is going to give us the 24250. Okay, and then we look at the last corner point, 32 and 60. That would be 200 times 32 plus 270 times 60 gives us 22600. And remember, the whole goal of this is to maximize the profit. Where's the goal again? Maximize. So we look for, to maximize, we look for the biggest profit. So in that case, we go through these values and we look for the biggest one. It happens to be this 2, 4, no, it's not that one. 2, 4, 300. So you go through and you look. So there is your maximum. So that means your optimal solution of your profit is 24,300, where your basic feasible solution, or in other words, your decision variables are going to be 0 and 90. So the optimal solution is where x is equal to 0, y is equal to 90, which gives you a profit of 24,300. Okay, so let's actually write that down. So the max occurs at P090 equals to 243,000, which means the optimal solution is your x, what was your x again? So a reminder, your x represented the number of H2 phones, where x is equal to 0, y is equal to 90, where x is the H2 phones, so you produce 0 H2 phones, and y is the minus phones. So you're going to produce 90 minus phones to get you a profit of 24,300. And that is it. You're done. Okay, so let's just put this in a graph in the Desmos graphing calculator. Again, you do this by hand, but obviously it's a lot clearer for you to see it if it's in the graphing calculator, because you can see all the differences and we can actually show you what's going on. So you would plot all your constraints. So we've gone through the process of how you plot the constraints. Just bear in mind that when I do it on the Desmos calculator, when I put in a constraint and when the constraint is supposed to be greater than or equal to, or less than or equal to, I put in greater than or equal to, and that is purely so that I have everything that is not feasible for that constraint kind of like scratched out, in other words, shaded. So my feasible region ends up that nice white like look. So we're going to do that maximization problem with ZZ Electronics. And the first constraint was 10x plus 8y is less than or equal to 800. So we're just going to plot that on the graph. So there we have the graph. Let's just zoom out a bit. So you would have your 0, obviously, and 100 and 100. Let's zoom in a bit more so that you can see clearly. So we have that first constraint. Everything in the red is not feasible. Everything in the white currently is feasible. So we have the next constraint, and the next constraint is 3x plus 4y is less than or equal to 360. And again, just bear in mind, and I'm doing it on the Desmos calculator, I'm do the signage in the opposite direction. That's purely so that everything that is not feasible is shaded in. Okay, so we add the next constraint into that. Again, everything in white is currently feasible. Everything that is shaded in is infeasible according to our constraints. So we're adding the third constraint, which is y is greater than or equal to 60. Okay, so currently again, everything that is white is feasible, everything that is shaded in is infeasible. And then we have to add in our two non-negativity constraints, which is x must be greater than or equal to 0. So it reduces our feasible region there, and y must be greater than or equal to 0. That doesn't really do much for us, it's just chilling over there. Okay, so now we have obviously those 4 corner points. And we investigate those 4 corner points for our optimal solution. But one of the things and one of the reasons why the corner point theorem works is because the objective function is going to end up being tangent to one of those corner points. Actually, can be tangent to 2 if it has both a min and max, but let's just go with it. So the idea behind this is that we will have the line of the objective function, which is 200x plus 270y. And we can have it with obviously the profit being 0. And if we do that, so we just plot that line there, we have this orange line appearing. Okay, so we have this orange line. Then what's going to happen is, as we increase obviously the y-intercept, which is the profit in this case, it's going to come closer and closer to our feasible region. And what's going to happen is, it's going to become tangent to the feasible region. So we have that point over there, that's 60 and, well, that's y is equal to 60 and x is equal to 0 situation, or 0 and 60. That is actually an optimal solution if the problem was minimized. Okay, so the first point that is tangent, where the objective function is tangent to the feasible region, is like the minimization optimal solution. But obviously we're doing a maximization problem, so we need to continue on. So now you're going to see that as we continue on, the next, corner point that objective function reaches, it is not tangent to the feasible region. It is going, like the objective function is cutting all the way through it. So it's not an optimal solution because it's not tangent to it. So what's going to happen is the extreme points where your objective function is tangent to your feasible region, those are the ones that are optimal. So we're going to move on. So we continue on, and we're sitting at that point over there. And now it's not that clear, so let's zoom in a bit. Okay, that's why this is useful. And you'll see that, okay, firstly, it's not exactly on the point yet. And we can't really get there. But the idea is that when we actually reach that point over there, it is not tangent to it yet. So we actually have to continue onwards. So let's then continue on and look at this point. And again, okay, so there we go. It is directly on that point, and you can see that it is tangent because you can see that it's basically not, going into the feasible region. It is lying directly on that constraint line for some of it, and then coming off. So we know that that point over there is going to be our optimal solution, particularly for our maximization problem. So let's just zoom out a bit so that you can see. So we have our feasible region. We have those 3 corner points. We check them manually, but if the whole process, it's actually showing us that the objective function is tangent to, the feasible region.